We're doing this video because this is a question that everyone asks. This is a common, kind of misconception to say if one type of testing doesn't work, then you assume, well, you mean everything? This only pertains to low frequency pressure, diaphragmatic testing, and Ron will explain.
Right. Well, there's two different kinds of testing, James. There are two different types of absorbers. One is the lint bag style. Okay. This doesn't refer to that.
Okay.
This only refers to absorbers that are made from a hard surfaced diaphragm.
Okay.
So like a plastic or metal diaphragm. Okay. And it's in a sealed box.
Okay.
So if you take a box, seal it up, fill it with fiberglass, then put a diaphragm on top of it and seal it. So it will only diaphragm at certain frequencies. And that frequency is dependent upon the depth of the box.
Mm-hmm.
Okay. We have found that the difference in the thickness of the diaphragm has little to do with what we're seeing.
Okay.
So, you don't want to go crazy and put a half-inch piece of steel on top because it's not going to diaphragm.
Mm-hmm.
But the difference between, say, 22 thousandths or 32 thousandths or 16 thousandths doesn't show up all that much, except maybe in the efficiency.
Okay.
Okay. And also venting the box doesn't seem to make that much of a difference. It broadens it just slightly, but it's not worth the effort.
Okay.
That's the best way I can put it. Okay. So we brought you in because we're going to share some stuff today that is not available yet because it's graphs of some of the research that we did with the gentleman who paid for all this testing. So I can't officially put it out there. So I would appreciate it if you wouldn't copy the graphs until they are released. And they will be released in a full report, which is around 7 to 8 pages.
Okay.
Okay, this will be just one page of it. Okay, and we're also not going to probably share what the total amount of savings are because that's the official report.
Okay.
All the stuff we're looking at right now is not officially reported or not officially supported by STM because you cannot
STM,
measure.
Sorry.
ASTM.
Oh, ASTM. Okay. Yep.
Yeah, it's not supported by them, and here's why: we're measuring individual items.
Okay.
Okay, it's not a general thing. Okay, so the official report should only allow reporting of the amount of savings per item.
And when you say per item, are you talking about per unit, or are you talking about like per area?
No, per unit.
Tested, and it's the area of that unit, only a unit, and it's not
only
the
that
state area.
Okay.
Yeah. So what we're trying to do here is one of the things that people don't understand is in order to be able to measure absorption, you have to be able to move the room enough to be able to measure it, the time difference. Okay. And in our case, it takes about 120 square feet of stuff to move the room.
Okay.
Okay. So if these things are 48 by 48, that's 16 square feet. So it takes, 8 to 12 of them to be able to move the room. So then the question becomes, how do you group them in order to be able to measure it? And that's what we're going to go over today.
Okay.
Is how this grouping affects what you're seeing.
Mm-hmm.
Okay. And I will try to explain these graphically with my voice. Okay. But in reality, we have photographs of all these setups.
Okay.
And they will be part of the reports as well. Okay. But so you're coming in kind of on the bleeding edge here. We're actually looking at this now as creating an addendum to C423 on how to test diaphragmatic absorbers in modules. So it will become a separate part of the standard.
Okay. That's
exciting. Well, that's part of what I do. I'm the task group leader of C423 and for E90. So, we see all this stuff all the time, and we're always writing new things and upgrades to the standards. That formula that we talked about for spacing is also going to be included in that as well.
Okay.
So that you can actually use this data in real life. Okay. Data has its own uses. And the problem is that sometimes people lose track of the fact that it gets used by other people for other reasons. Okay.
Yes.
So, the idea behind ASTM was to provide a way of measuring things that's common for everything so that it's comparable for the manufacturers. That's what it was designed for, is manufacturers. So they can sit there and say, okay, this item matches up to our item by like this. Okay.
And as an aside, at some point, the value of your lab and its size and the modal overlap down in the frequencies that we care about in audio. But in smaller rooms, you don't have that modal overlap. At some point, the physics are the same, right? The physics of what the thing does in the room are the same.
That's right.
But with the lack of modal overlap down that low, is the practical use the same? Okay.
Yeah. In this situation, there's a difference between measuring it and using it.
Yes.
Okay. Measuring it, it takes a certain criteria to be able to measure it accurately. When you put it into a room, it's going to perform that way no matter what. Okay. But we may not be able to measure it in that room.
Right. So
Okay.
this,
And
I'm trying to tell people for a long time, you can't measure it there. You may see a difference or hear it. You'll definitely feel a difference in the low end and how the decay works. But measuring those, whatever it is, there's actually no standard for it in these small rooms, especially in a treated room.
And I think that people we generalize terms so much that your use of the word, it will perform the same way, maybe is probably much more a rigorous definition of will perform the same way than what the layperson may be thinking.
Let's put it this way. The idea here is when you design a room, you will at some point figure out that you got let's say a problem at 125 hertz. Okay. You're going to look at what the reverb time is at that point in time. Or in this case, it may not be a reverb time. It may be a decay time. There's a difference. Okay. But the point is, you're going to calculate at some point how many sabins of absorption you're going to need to absorb that particular peak. And that's calculable in your room.
Even in a small room?
Yes, in any room.
Okay.
Yeah, the idea here is you know how much total absorption is, you know how much you have to reduce it by, and you can calculate that by frequency, by just calculating how many sabins you need. So if the whole room has this many sabins and you need to reduce this by this much, then you can look at the percentage of it and calculate that number of sabins.
Yeah, look at the sabins per third octave band, and I need this here, I need that there, I need this many here, and you get that. And it's right.
And that's what I've done for my room based on the measurements I've taken, and actually have a weird dip in the decay at 125.
Yeah.
And trying to figure out how to bring down everything on the other sides of it properly.
Well, okay. First thing you have to figure out is what's causing the dip.
Yeah.
Because that could be how you're measuring it. Okay. Because one of the things that happens is microphones get moved in areas where you have modes, which 125 hertz is notorious for. Depends on where that microphone is in that mode. You may be looking at the bottom of it or the top of it.
It was across about 40 measurements with speakers and microphones in top and bottom corners, left and right.
But see,
different speakers, and I changed heights as well as listening position measurements.
Here's the problem. As soon as you said multiple speakers, you have built in automatic.
One speaker at a time.
Okay, thank you.
I used the subwoofer. I used PMCs. I used some others.
Right.
Because I don't have a dodecahedron speaker. Yeah, I don't have an omnidirectional speaker.
Well, you do, believe it or not, you just don't know you do.
Okay.
Okay. It's called your voice.
Okay.
Yeah, your voice is mostly especially at lower frequencies, it's basically omnidirectional. By the way, that also occurs with a subwoofer.
Okay.
Yeah, just take the subwoofer and you can shove it into a corner. Okay. Don't face it outward, face it inward.
Yep.
Okay. And it'll act like an omnidirectional source. Okay. And if you want a higher frequency that has an omnidirectional source, you put yourself in a compression driver in a slot, like a diffraction slot.
Okay.
And that'll give you an omnidirectional source too. Okay, it's not that hard to do.
Okay.
So these are all little things that people don't they don't think about, because it's like, well, we got to have something special. No, you don't. All you need is a nice compression driver. And if I were in your shoes trying to do something like that, I would seriously consider doing something like going to Brankus and asking for their 4-inch driver.
Hmm.
Okay, and then put a compression slot on the or actually, you could probably in this situation ask them to give you a 160, what they call 160 complex conic horn,
Okay.
and it will act like an omnidirectional speaker from about 200 hertz up.
Okay.
Okay, I mean,
Cool.
there's all kinds of good things there out there. Okay,
Yeah.
but in the meantime,
Yeah, this is not a room consult for me, but
right. Yeah, but
yeah.
just keep this in mind, that this is something that is one of the problems is measuring rooms.
Mhm.
Okay, if you don't know how to measure a room, you can get all kinds of weird things,
Mhm.
and these dips do appear just because of the fact of the size of your room. Okay, and there's no way around that. That's just that. And now the question becomes, if you take down the frequencies on either side, does it really come down to where the 125 is, or does the 125 drop with it?
Yeah, and that's
And that's what usually happens. Okay.
most of what I'm looking at is the rigid fiberglass stuff,
Yeah.
and or these real acoustics for the low end. So
Well, and that's the whole point is the things like 125 hertz, or let's say you're looking at 200 or 160 to 200. Okay, your best option, believe it or not, is the limp bag absorbers from MBI.
hmm.
Okay, they really, especially the 6-inch ones, cover the frequency range of roughly 100 hertz to around 250.
Okay.
Okay, if you want to get a specific one, you get a 2-inch one, and it covers the range from about 160 to 250.
Okay.
Yeah.
Okay,
Those are targeting. That's targeting an area,
right.
I'll use those, if I may add, after I've done all the calculations, and we got
Right.
Owens Corning Pink in broadband absorbers. You know what that does? Has absorption coefficient of over 1 from 80 hertz to 500 hertz.
Mhm.
Really nice
Yeah.
peak in that area.
Yeah, it's good. It's good stuff. Yeah, but here's how you tune it.
Mhm.
Okay, and this is the hard part. If you have something like the MBI Bandit, and you wanted 6 inches, which covers that big wide range, but you don't want to get rid of the 125 hertz. Okay, you'll put a grid in front of it that blocks 125 hertz and allows the rest of it through on both sides. So it's what
that's where my head had been going, but my knowledge of what that grid would look like is not. I'm not that deep into it that I could figure that out. It
yeah.
seems a band, not pass grid, but a band.
Actually, what you're saying is true.
It would be a band pass to the absorber.
On both sides.
Yeah,
sides.
okay.
Okay, you have a band limited absorber is what it
Yes.
is.
Yeah.
Okay, and putting wood in front, depending on how you face it and stuff, you have to think a little bit about what quarter wavelengths and what eighth wavelengths are, to be able to figure out how wide the board should be
Okay.
to go in front of it. And then you have to leave
spacing to let the proper amount through.
Yeah, and believe it or not, some of that's going to take experimentation. One of the nice things about the laboratory is I can experiment to my heart's content as long as I have the money to do it. Okay, but the facts are I got to pay somebody to do some of this.
So honestly, years ago, one of my bucket lists, if I'd ever won the lottery, was to do exactly what you're doing, John, is to take all of this stuff and just spend millions of dollars in a lab for the home builder.
I'm getting there.
Honestly, that's I really have gratitude for what you're doing, because it's what I had always fantasized about doing.
Well, and the problem is the industry will not pay for this kind of stuff, because
exactly.
there's nobody in the industry that is interested in this stuff. This is people like us that do this. And please understand where I come from. I'm not a laboratory guy. I opened a laboratory in self-defense. Okay. I was a consultant for 45 years, and I designed opera houses and stadiums and big facilities. I didn't get into the small facilities because they're a different world. Okay, but the basic laws of physics still apply.
Yeah.
And so that's where I come from. And what happened was I was designing big churches, huge churches, that I would design them and they would say, well, the reverb time is going to be this. And when I actually built them, they weren't. And I kept wondering what the heck is going on. And I started realizing that the databases in these programs is incorrect. And I was a great believer in this whole thing that people said that you can't have a coefficient above 1. So I believe that, and I ran with it, and I taught with it, and I did everything else for years. Okay, and when I opened up the laboratory, I started actually doing some testing and realized they are real. It's just that there's a bunch of idiots out there that don't want to admit they made a mistake in 1928. Okay, and that mistake was trying to define that number as a coefficient. That is a mathematical construct that has nothing to do with physics. And so I always tell people, no, it's not a coefficient. It is a constant, and constants don't have the limitations of a coefficient. And that's because mathematicians are weird people. What can I tell you? Okay, but they have to live with the rest of us. The problem is that when you have something that has existed for over 100 years, trying to change it is like trying to move the iceberg out of the way of the Titanic.
My dad before he died, he was a statistical quality.
Yeah, you understand.
and he would either say your measurement is wrong or your model is wrong. If
That's right.
What you're measuring is not matching what your model is, then you adjust the model or you adjust your measurement.
Well, the problem is measurements are harder to adjust because they don't change.
Well, I mean, figure out a different methodology.
Well, actually, the only answer is to change your model.
Yeah.
Okay. When we worked at NASA, we had to calculate a whole lot of times about changing the model of how we put rockets up on the moon. Okay, that changed a whole lot. I've got what do you call it? Wind tunnel models of the shuttle. That if you ever saw these, you would look at it and go, "That doesn't look anything like the shuttle." No, it doesn't, because we had to change it in order to meet a whole bunch of other specifications that were required, not just aerodynamic, but cargo carrying and stuff like that. So those other things changed the shape of the thing, and it was kind of like this was the best,
compromise.
Best compromise you could get, and still make it fly. It was kind of like a flying brick, is what it really was. But if you ever saw the models, I have these models in my boxes stored away for 25 years now. They look much sleeker and much more real, more like science fiction type stuff. And they flew. The problem was they didn't carry anything. they were like, a bat wing basically. Yeah. And so it was one of these things where I looked at this and my first thought was, yeah, we put it in a wind tunnel and it flew quite nicely, but that wasn't all it was intended to do. And, it had to hold people as well, and this thing wouldn't hold people either. It was just a flat wing is all it was. And it was like, okay, so if you ever see these pictures of things look like a triangular wing that has no body to it, that's what the original space shuttle originally looked like. Okay, wow. Very efficient looking. So what we ended up with is like, this is what you end up with when you send a scientific model to Congress and then let them figure out how to do the reduce the cost on it as much as possible. Okay,
you get a flying brick. Yeah,
that's basically it. So, but so we're kind of in the same situation here, and that is we have looked at absorption as being really only one thing for years, and that was based upon fibrous materials. So if you can look back at Sabin's original measurements and observations, they occurred in a large room in, I think it was in Boston, at the laboratory, or is it Princeton or Harvard? I can't remember which one it was at. But it's where he first discovered that if you take things out of the room and put things back in the room, you can change the reverb time of the room. Okay, that was the first observation. And that's really what he did. Okay, people forget that there's two Sabins. Okay, there's Wallace, which is the guy who invented all this stuff, and there's nothing wrong with what he did. What he did is he made it possible to measure the effects of absorption. And that's all we can do. We cannot measure absorption directly because it's too small an amount. The change in energy is so tiny that it's virtually unobservable unless you do it in large quantities, which is what happens in a room like this. Okay. So all we can do is say, okay, if you have a room that is absolutely hard and has no absorption of any kind, okay, then you measure what the reverb time in that room is. And now you put your sample in and you make sure the sample is large enough to be able to move the room significantly enough to be able to measure the difference. And at that point, you take the difference, calculate that time, and then you can calculate the number of Sabins that is in that sample. And that's what the basic idea of measuring absorption is we're just observing the effects of the absorption, not the absorption itself. So,
and it's the effect of the absorption on the decay time.
That's right.
Not necessarily the initial frequency response, because you're in a diffuse.
Forget the frequency spot. It has nothing to do with it. Just has to do with just sheer decay time is all
just
it is.
Clarifying for myself.
Yep. So that's all it is. We're just looking at decay time. And that's the right word to use, by the way. Reverb time is based upon other things, which is misused big time in our industry. Okay, so let's talk about decay time. So so you measure that difference, and then from that you derive the amount of absorption using these Sabin formulas. Okay. The problem was that 25, 30 years later, Paul Sabin, who is Wallace's nephew, founded Riverbank Laboratories. Because Wallace did not. Wallace had nothing to say about it. Okay, but Paul founded it, and the problem is that Paul is not quite the genius that his uncle was. Okay, he was a good guy, very observant, but he jumped to conclusions really easy. And so he presented his first paper in 1927 at the ASA meetings, which is the first ASA meetings. And there was another gentleman that was one of his compatriots. And in our industry, by the way, compatriots means, an enemy who doesn't have a gun.
Contemporary, yeah.
Yeah, but the point is, he didn't agree with Paul. Okay, and he was an acoustician too. Okay, so there's a lot of people who didn't agree with Paul. And Chrisley was his name. And when Paul presented his paper on how to create some kind of a thing that you could use to calculate absorption, he came up with this idea of a coefficient. And his idea was, well, okay, full absorption is a 1, no absorption is a 0. So that's a coefficient. Therefore, everything should fall between that. And based upon his ideas, if you take the amount of absorption in the sample and divide it by the square area of the sample, then you have a coefficient. The problem is, the first time he measured something that was more absorptive than the sofa was, he got a number that was above 1, and therefore it became already known as okay, because all of a sudden it was like, it doesn't work that way. Well, why didn't it work? Well, there's other effects involved, edge effects. Okay, he's the one that invented the name edge effect, because he was trying to explain why the edges would be more absorptive or whatever, and he really had a hard time with that one because he never did straighten that one out. But you have to understand, people back in those days were not nearly as polite as they are today. Okay, not even close. I mean, today we'll say something like, well, our esteemed colleague doesn't understand this or something, and here's a theory that he doesn't quite understand what he's doing. That's what we would say. Okay, Chrisley had his paper right after Paul Sabin's, and it's written. You can read both these papers. They actually published the papers at that time on the meeting proceedings. And Chrisley started his paper with Paul Sabin's idea of using a coefficient is pure. I tried to remember the way he described it. It was equivalent to bullshit. Okay, and Paul is an idiot for suggesting this, and he said that in his papers. He was an idiot for suggesting this. Okay, so there was already a lot of not good feelings going on in that meeting all the way through the whole meeting. It was really entertaining to read the whole thing, but I realized after that, it was like, wow, they would never survive in today's world with all the politically correct functions. they called it as they saw it, but it was already a problem as far as the coefficient. So Chrisley had already said that it needs to be a constant, not a coefficient, and that it could be supported in that way, but not the other way. And it was, they had a vote on it. They decided that ASTM was founded right about that time, and they decided that they were going to use Sabin's because of his name. So, and that hasn't changed in all this time. So, okay, but just we wanted you to understand that back in those days, the only absorption that was really observed was the fiber absorption, which is like fiberglass, where you have the sound going through it, slowing down by the friction going through the fibers. And anytime you change energy by slowing it down, you convert it to heat. May not be able to detect the heat, but that's what's happening. And any conversion to heat is absorption. So you have to keep that in mind, any conversion. Okay.
One thing you may, just as someone who's studied this on my own, one thing as you're educating people, the difference between slowing down with particle velocity, conversion to heat, versus the speed of sound transmission through the fiber. It took me a while to wrap my head around that those are two different things.
Yeah, the speed of sound is determined by the atmospheric pressure. That's it. That's all determines it. So that's how fast sound travels through the atmosphere at that time. Now there is a particle velocity involved because people and particles are invented by physicists to describe how liquids. When I say liquids, how to describe everything in a way that is mathematically capable of being moved around. So you have to convert something into a particle or into a wave or into a liquid or whatever. So it's a medium is what it is. And the problem is mediums are homogeneous.
Gotcha.
Okay. Therefore, it's hard to, you can't say, well, homogenously, this thing moves this way. There's too many other things that affect it. So you break it down to the smallest particle thing, and we could say, okay, it's a molecule of air or a molecule of water or whatever. Okay. But the idea is we named it a particle. Okay. And doing so, now we now say the sound has a speed that is based upon the particle's velocity. Okay, that's the easiest way to describe it. And so therefore it is now able to be slowed down by something else because it runs into something.
Gotcha.
Okay. And we all understand, the laws of conservation of energy and stuff. If something hits something, it slows down because it loses energy. And that's just a simple way for physicists to explain how it works. In reality, it doesn't do that, but that's what happens. Okay. So and if we get that deep into physics, now we lose people big time because they kind of look at us like,
I tried to explain that several years ago when people were talking about the sound slows down and therefore your resonances will change and the pitch and all that. That's, as you just described, that's how it's described.
Yeah, it's the wave front, not the speed of sound.
Yes.
The speed of sound remains the same, but the sound wavefront is different than the speed of sound.
Right.
The wavefront will move at that speed. Okay. But inside that wavefront, you have different densities of molecules. Okay. And it's pretty hard to describe what's happening inside that density. That separate. So you have a heavy density versus a light density. Does the speed of sound change? No, but the speed of the particles in that wave front do.
Sure.
Okay, and that's the difference. You just have to be able to visualize that. And one of the reasons I got into this business, and people tell me that I'm able to educate about sound, is I see sound. That's the best way I could put it. Okay, I actually see sound. And it was interesting. Somebody told me that's kind of like Einstein talking about he could see time and gravity. So when I go into a room, I can actually see what's happening with sound. I can see the wave fronts and all the other stuff moving around. How do you teach something like that? You don't. Okay, that's just something that is a gift that was given to me, and I have to live with it. But I also have to figure out how to use that to describe to other people what is actually happening.